today is kind of a standalone lesson, meaning everything we talked about yesterday with regards to simple harmonic oscillation is leading somewhere specific, to masses and springs and then eventually to waves. What we're doing today with masses oscillating on springs, I call it a standalone kind of lesson because it doesn't really go anywhere. And the difference is, I'll tell you why we're doing it if it doesn't go anywhere in a second. The difference is the mass on the oscillating spring in these questions today, in this situation today, will be horizontal. We're going to be looking at a mass on a spring that's bouncing back and forth horizontally so that we can ignore the force of gravity. It makes it easy. The reason why we're doing this is it's a very good opportunity for us to practice working with conservation of mechanical energy. It turns out that the problems we did with a roller coaster, or better yet, a pendulum swinging back and forth, and the fact that the pendulum has potential energy at the top and kinetic at the bottom, it's exactly tied to what we're doing today. So we're going to be describing the energy transformations that occur when a mass is at the end of a horizontal spring, and we're going to be applying conservation of mechanical energy to these situations. So when a mass is oscillating on a horizontal spring, the force on the spring by the mass and the force that the spring exerts on the mass varies. You know, what I would like you to do is imagine, and we have diagrams that I've created for you, but imagine right now that we have a frictionless horizontal surface. I have a wall that I have connected a spring to. And let's just say for the time being, 1, 2, 3, 4, 5, 6, 7, 8, 9, that this that I'm drawing, and you don't need to draw it, I've got better diagrams printed for you, but I just want to talk about what's going on here. This is a mass that the spring is glued to. So the spring is connected to the wall, it's connected to the mass. The mass is on a frictionless surface, and this is the equilibrium position. You know, a reminder from yesterday, where is the equilibrium position for this mass in oscillation? The answer to that question is, it is wherever the mass will be if there's no oscillation. This is the equilibrium position. So this mass right now is at the equilibrium position. If again, it's printed out, but I would rather draw this, and I think you get something from seeing it drawn just in case you need to sketch something. If I take that mass and I pull it over here, now keep in mind it's attached to the spring, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. If I take that spring and I now stretch it, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you count the coils, it's the same number of coils here as it is here. Okay, you get the idea here? That I pull this out to here and I let it go. What's going to happen is that spring is going to be pulling the mass back to the equilibrium position. I hope you understand when the mass gets to the equilibrium position, it's not going to stop. It's going to keep moving past the equilibrium position until the spring gets really compressed. And then it's going to spring back and repeat. So it's going to be a harmonic oscillator back and forth. But the point is this, that when I release it, at that instant that I release it, is there a force acting on the mass by the spring? Yes, the spring is pulling it back to the left. A short time later, the mass will be here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Not quite at the equilibrium position, and not where it was here. It's a little bit closer. Will there be a force acting on the mass at that point? Yes. But will the force on the mass at this point be the same as the force on the mass at this point? No. Why? Because of Hooke's law. the displacement of the mass from the equilibrium position here is greater. So you are going to have a force acting on the mass. We call it a spring force. I mean, I'm not going to bother writing it. You have a spring force acting on the mass that's calculated by using kx. And we disregard the negative. Remember that? I don't want to worry about the negative. If you want to just briefly understand that, the displacement of the mass right now is to the right, but the force is to the left. That's where the negative comes in, which is not relevant. It's not necessary. When the mass is here, the force acting on it will be less because x is smaller. You get the idea here? What I'm telling you on this first little page is that the more the spring is stretched or compressed, the greater the force on the mass. And all that is Hooke's law. But because of that, what's going to happen is the acceleration of the mass will always be changing. I might be getting a little bit ahead of myself, but when you take a look at this mass at any particular point in time, the force of gravity and the normal force are exactly equal but opposite, which means the net force acting on the mass is that force that the spring exerts on the mass. And if the force changes, then the net force changes. And if the net force changes, the acceleration is different everywhere. In other words, you cannot use kinematics formulas here. Those kinematics formulas are only good for a constant acceleration. Okay. Let's take a look at all this information I'm giving you for the warm-up. First of all, we're considering a mass oscillating on the end of a horizontal spring. This is the diagram we're looking at. Okay, this is already printed for you. But the difficulty with this is it's one particular snapshot, right? This mass is bouncing around. Obviously, a printed picture is not going to show a whole bunch of things in motion. What is important on this is that the mass of the spring, or the mass on the spring, is at a particular point in time in this picture. It happens to be not at the equilibrium position and not furthest away. So let's talk about the notation here. The arrow indicates its position. So in this diagram, this arrow is simply telling us where the mass is. It's etched on the aluminum block or whatever it is. It's written on there. It's spray painted on there. It's whatever. Different displacements of the mass are labeled. Whenever you see a displacement of 0, that's the equilibrium position. So right now, if I said to you, with this vertical mass that you're looking at in the classroom, which is obviously different than what we're talking about, what is the displacement of this mass right now? 0. Because this is the equilibrium position. That's different than a Hooke's law application where we say, this is the equilibrium position, and we're talking about forces. So the equilibrium position of a mass oscillating on a spring is the position of the mass when it's not oscillating. When again, I'll do the same thing I did yesterday. We'll just say that the middle of the mass is at my microphone. Is that pretty close? So when this is in oscillation, the distance it goes below is what we would call a maximum displacement. And I don't know if you remember this from yesterday, but maximum displacement is called amplitude. On this diagram then, the negative A is the amplitude to the left of the equilibrium position. The positive A is the amplitude to the right. So this arrow is going to be oscillating. I won't move the mass, but this arrow is going to be oscillating from here to here to here to here. And because it's frictionless, and we're assuming that there's no friction even in the spring, which is ridiculous. As soon as you have metal that stretches and compresses, it heats up. You lose energy due to friction. If you don't believe me that bending metal will produce heat, take a piece of a coat hanger, a metal coat hanger, and bend it back and forth even 10 times, and then find your best friend and touch their hand with it. Don't do that. You burn them. It gets that hot. It's very, very warm. Once again, giving good ideas to students. So, what are we asked? show that the magnitude of the net force acting on the mass at any point in time is the restoring force of the spring. Well, that's easy. The net force will be equal to the sum of all of the forces. It will be the spring force, it will be plus the force of gravity, it will be plus the normal force. So how on earth does this become the statement that F net equals Fs? How does that happen? Well, it happens because the gravitational force added to the normal force gives you 0, because they're equal in magnitude but opposite in direction. So these two, I didn't leave myself too much room here, but you have room on your handout. These two add to give 0. Now, if we were talking about a vertical mass spring system like this that you're looking at in the classroom, that gets more complicated. This is one of the reasons why we are looking at horizontal. Because here, the vertical force is a result of the spring force and gravity acting together in different ways at different times, and it gets very, very complicated. Explain why the acceleration of the mass is not constant. Well, acceleration is equal to net force over mass, but in this particular application, the acceleration is the spring force over the mass. Right, we just established that up here. But the spring force, and whenever I talk about the spring force, I neglect the vectors, and that's what we're about to do right now. I'm not going to put the vectors in anymore. The spring force is equal to the spring constant times the displacement over the mass, but the displacement is always changing. The displacement is how far away from the equilibrium position it is. And the equilibrium position in that diagram is the dead center between negative A, and the mass is bouncing back and forth from A to negative A, back to negative A. So the displacement's always going to be different depending on where the object is. And if the displacement's different, the force is different, and the force is different, the acceleration is different. What two types of energy are present in the mass spring system? Well, is the mass ever moving? Yes. So there's kinetic energy. What other type of energy is in the system? And I want to talk about something right now, that if I go back to this diagram, would you agree that where that red arrow is right now, that's the point in time where the mass goes from moving to the right to moving to the left? So what does an object have to do to change direction? It has to stop. At that instant in time when the mass is at A, or at negative A, there is no kinetic energy. And yet a short time later, there's kinetic energy. Which means as the mass starts getting closer to the amplitude, to capital A, what happens is its kinetic energy is being lost, and then it comes back. Which means the kinetic energy is being stored somewhere. Where is it being stored? Potential, exactly. But it's not gravitational potential. It's elastic potential, or spring potential. And there's nothing wrong with using the word elastic. You can use spring there if you like, but they're interchangeable. An elastic band is spring-like, and a spring is elasticy. They both have the same physics. They both follow Hooke's law. So those are the only two types of energy in the system. If there's no frictional forces, what does that tell us about something that remains the same regardless of where the object is? In other words, what's conserved? Mechanical energy. E mechanical remains constant. I won't even put equals. Remains constant. And I really want to cut to the chase here. What this means is that for this mass on the spring, EK plus EP elastic at one particular point in its oscillation must be the same as EK plus EP elastic at any other point. Just like a pendulum, when the pendulum is swinging back and forth, we know that the total mechanical energy at the top and the total mechanical energy at the bottom and the total mechanical energy anywhere in between is always the same amount. There was a question, everybody, on your exam, and I'm going to make up numbers because I don't have it right in front of me. I do, but I don't want to bother to look. You were told that at one particular point in time for a pendulum, this is for a pendulum, that the object had, I'm going to say 1.6 joules of potential energy, and it was moving at that's a pretty big number, it doesn't matter, at 2 meters per second. And I'm going to say that the mass of the pendulum was 0.8 kilograms, okay? And somewhere in the question you were told that this gravitational potential energy was measured relative to the bottom point. And the question was, what's the speed? What's the maximum speed? I don't think it was phrased this way. I think it said, what is the speed of the pendulum at the bottom? Does that vaguely ring a bell? Okay. The idea here, and you guys did very well on this, is that you know the maximum speed is the speed at the bottom, and you know that at the bottom, the mechanical energy is only kinetic energy, right? Whereas up here, the mechanical energy is potential plus kinetic. And to solve this problem, you used the law of conservation of mechanical energy. You said that 1.6 joules plus 1/2 mv squared with 2 meters per second will equal 1/2 mv squared at the bottom where there's no potential energy. What that is like, everybody, is me in this picture telling you how much potential energy there is here and telling you the speed there, and then asking you for the speed here. Because at the equilibrium position, there is no potential energy because the displacement's zero, the force is zero, there's no elastic potential energy. Are you with me that it's the same as a pendulum? It's just that it's not swinging back and forth, it's oscillating back and forth. All right. I think we're ready to get to it. Warm-up number 2. The diagrams below show the mass at 4 different points or positions. On each diagram, label everything about the situation. Okay? So, at this point in time, and this is not just, we're not holding it there. I've pushed it into that point and I've let it go. And it's bouncing back and forth. And then when it gets back to this place, I've taken a snapshot. What do we know about the displacement? Well, the displacement is a maximum. Definitely, right? Are you with me on that? Okay. That means that the force is a maximum. And I'm about to tell you something that may cause you to get confused, but you got to fight your way through it intellectually. That means that the acceleration is a maximum. Because that force is the spring force, which is the net force. Right? If the net force is as big as possible, the acceleration is as big as possible. And that actually shouldn't rock your world. That should make sense. But what's weird and where the conflict comes in is we also know at this point it's not moving. Because it has to stop to change direction. So the conflict in your brain is the left side of your brain is saying, well, it's accelerating at a great rate, but yet it's not moving, the left side says. And you get this internal conflict. But this is an instantaneous acceleration. If you have ever been on a ride at, say, the Calgary Stampede or the Edmonton Exhibition, Klondike days, where at some point in the ride you move in one direction and then you stop moving and move in the other direction, the point in time where your head gets whipped around the most is when you stop. When you stop, that's where you can get whiplash. That's because the acceleration of your head is as great as possible. The other thing we want to add here is statements about energy. That EK is 0, that's a K, and EP is a max. Capiche? I don't think there's anything we really need to say beyond that. We've talked about the displacement, the force, the acceleration, and the energies. By the way, we can make a mental observation here that this potential energy that it has at this point is the mechanical energy in the system. Because mechanical is kinetic plus potential. And there's no friction, so it's the same amount all along its path. So whatever we get when we add these two energies together, this will be the mechanical energy, whether it's there or anywhere else. Which means the potential energy there is the mechanical energy in the system. When the object gets to here, what we know is that the displacement is 0, which means the force acting on it is 0, which means the acceleration is 0. And when I say the force, I mean the net force, I mean the spring force, I mean the applied force. They're all the same force. What's maybe counterintuitive is the right word. What's maybe counterintuitive here is that the speed is the maximum speed. Very similar to that. Remember when I had the bocce ball hanging from the rope from the ceiling, we had the pendulum? When the bocce ball gets over to this point, where my nose is, it's not moving very much and then it eventually stops. However, if I were to be standing at the bottom or standing in the middle, when that bocce ball comes down, if it hits me in the thigh, it's going to really hurt because it's moving the fastest at that point. But at that point, there's no potential energy. It's all kinetic. Same thing here. The counterintuitive part is in the middle, there's no acceleration and yet it's moving as fast as possible. You can't equate acceleration with speed. By the way, here the kinetic energy is a maximum and the potential energy is 0. And I don't need to write elastic potential energy. What else would we be talking about in this situation? And I want to point out to you that the sum of these two has to be the same as the sum of these two, which means that this has to be equal to that. Just like the potential energy of a pendulum at the top is equal to the kinetic at the bottom, the potential energy of a mass on an oscillating spring at the amplitude is equal to the kinetic energy at some other point. Not at some other point, at x equals 0. This one, let's just write that. Everything we said about the state of affairs when it's at negative A is true when it's at positive A. It's just the directions are backwards. What about here? Well, what we can say here is that the amplitude is not zero and it's not a maximum. It's somewhere in between the two. And what that means is that the force is somewhere between nothing and the maximum value. The acceleration is between something and a maximum value. But more importantly, and I feel as though this is really not important. I mean, I could say the same thing about the speed. The speed is somewhere between nothing and the maximum value. But more importantly, at this point, the mass spring system has kinetic and potential energy. When I say they're not equal to zero, I mean that there's some value for each of them. And whatever these two numbers are, when you add them together, you will get the same thing as adding these two numbers together, and you will get the same thing as adding these two numbers together. And then, that's it. Now, let's put this all together. And you know what? Maybe in summary, before I get to this first example, what we are saying is the potential energy at x equals a, the kinetic energy at x equals 0, and the potential plus the kinetic anywhere in between are equal. Right? I mean, I'm saying 1/2 kx squared can be equal to 1/2 mv squared if you're comparing the maximum displacement to a zero displacement. Or like the exam on your question, or the question on your exam, where you had potential plus kinetic equals kinetic, then it would have been, you were comparing these two positions in the oscillation. A pendulum is an oscillator. You didn't know that when you did that question on the exam, but it is. All right, let's try this now. A 60-gram mass is oscillating at the end of a spring, and we know the spring constant. We know the maximum speed. I think it's worthwhile to note that the maximum speed occurs where there's no displacement. It's at the equilibrium position. Determine the maximum displacement. Well, that's at x equals a. So here, the energy is all kinetic. Here, the energy is all potential. But energy is conserved. And energy is conserved. So however we calculate it, the energy at the equilibrium position and the energy at the amplitude will be the same number. Don't forget, EP for elastic from the previous unit is 1/2 mv squared. Sorry. Thank you. Don't forget, EP for elastic is 1/2 kx squared from the previous unit. I've taught you the physics. The rest is math. Can I cancel those halves? Well, of course. Why would you even include the halves? I can multiply both sides by 2. So I end up with, I want to give myself a little bit more room here. I end up with mv squared equals kx squared. So I can take the mass in kilograms times the speed squared in meters per second equals k in standard units times x squared. It's just a matter now of taking 0.06 times 0.15 squared and dividing by 2.5, then of course taking the square root. I don't know, I don't remember exactly what I said, but I fear that I might have said 0.06 times 0.15. If I did, I meant times 0.15 squared. Don't forget about those squareds. And I want to divide by 2.5 and then take the square root. So about 2.3 centimeters or 0.023 meters. That is the displacement that's the maximum displacement. That is A, if you like. What's the maximum acceleration? Well, do you agree this is always the case? And by the way, this is not circular motion, right? This is linear motion, back and forth. Do you agree that in this particular situation, this is the case? Because the net force is the spring force. That means this is what's going on. And I want to really highlight something, everybody. Up here, this is a statement regarding energy, whereas in B, we're looking at a force analysis, not an energy analysis. So just stop for a second and look up here. I know that many of you know how to get the answer. This is the case everywhere in the masses oscillation. If you want the acceleration to be a maximum, then you need the force to be a maximum. If the force is going to be the maximum, then the displacement has to be the maximum. So to find the maximum force, you use the maximum displacement, and we found that it's 0.023. So our acceleration will be kx over m, which is 0.0, which is 30, is it 32? It's 2.5 for k? I don't know where I got 32 from. 2.5 for k times x, not x squared, divided by the mass. I'm going to carry all my decimals. So I need to take the spring constant times the displacement. What you're looking at on my calculator right now is the maximum force acting on the mass at any point in time, and it happens at the equilibrium position. If I divide by the mass, I get the maximum acceleration of about 0.97 meters per second squared. Anybody else get that number? Okay. So the maximum acceleration is about 0.97 meters per second squared. Any questions with A or B on example 1? Okay. 2, a mass oscillating on a horizontal spring has a maximum speed of that and a maximum displacement of that. What is the mass? Well, I hope you equate maximum speed with the point in time where all of the energy is kinetic. And I hope that you equate a maximum displacement to a point in time where all of the mechanical energy is potential. In other words, if you go back, I'll just show you quickly. If you go back and you talk about this diagram, we are, for question 2, comparing these 2 points in time or these 2 positions, where we have only kinetic here and only potential here. And since mechanical energy is conserved, you set them equal to each other. Yeah? This is like saying, you know, the maximum height of the pendulum, what's the maximum speed? Except we're not after the maximum speed. What we are after is the mass of the spring. So we can put all of the numbers in, the halves cancel. We don't know the mass, but we do know the speed. It is 0.25 squared. Always use standard units. Equals the spring constant of 4 times 0.031 squared. A lot of questions with springs in oscillation due to a mass on them use centimeters and centimeters per second. You just have to be careful about that. It's very simple to solve this. Take 4 times 0.031 squared and divide by 0.25 squared. So 0.061504. Just double checking my calculator work. Does anybody else get that? Okay. B. What will the speed be when its displacement is 2 centimeters? So the thing to understand first, everybody, is 2 centimeters is less than the maximum displacement, but it's not 0. Which means we're talking about here this point in time, or this position, as being a situation where we have kinetic plus potential energy. And we can equate that to the place where it has potential energy only, if we like. Could we equate that EP plus EK, which will lead us to the answer, could we equate it to the point where it has kinetic only? Yes, you could. I'm just going with this. So this will be 1/2 kx squared, where this is the maximum displacement. This is 1/2 kx squared, where x is some number that's not 0, but it's not the maximum. Do you get my intention by writing that? It's just, it's a value, but it's not the maximum. Plus 1/2 mv squared, where, you know, the speed is some value. It's not 0, it's not the maximum, it's just some number in between. The halves cancel. I've said to you early on in the course and a couple of times since we started, physics is not math, but it turns into math, right? This is just a math problem at this point in time. Putting in the numbers, K is 4. The maximum displacement, is that correct for the maximum displacement, 0.031? Squared equals K, which is 4, times the displacement at this point in between the two extremes, squared, plus the mass, which we found to be 0.0615, I better look at this, 04, times v squared. So kx squared equals kx squared plus mv squared. You know, you should know how to solve this, but just bear in mind that this is just a number. It's just some number. This is just some number. So you have to subtract the two numbers and then divide by the mass and then take the square root. Four times 0.031 squared minus 4 times 0.02 squared. By the way, this is not the kinetic energy because we got rid of the halves. If I were to multiply this by half, that's the kinetic energy. Now we have to divide by the mass. and take the square root, and before I hit equals, the maximum speed, everybody, was 25 centimeters per second. Since this is what I call a meh point, the speed has to be smaller than the maximum speed. It's only about 19 centimeters per second instead of 25. And just to put a cherry on top of this, I think a really good kind of written response question and potentially a good exam question, multiple choice even, would be not to ask you A, but to ask you B. Well, maybe not. You could do B without, no, you would have to do A first, wouldn't you? Because you need the mass. So that would be a really good question, is if I just gave you that information and said, when the displacement is 2 centimeters, how fast is it moving? And you would develop this, and then you would start going through and going, well, I know the maximum displacement. I know the spring constant. I know the displacement here. Oh, I don't know the mass. So then you would equate the two extremes with each other so you could find the mass.